let's prove this limit. We have the limit of the rational function x over x squared plus 1 as x approaches 0 is equal to 0 using the definition. So the definition works like this: if for every epsilon greater than 0, there exists delta greater than 0 such that if x is an element of A is a subset of R, where C later on, in this case 0, is a cluster point of. And you have your x minus C is less than, absolute value is greater than 0, but less than delta. Then you have your f of x minus L is less than epsilon. We would like to achieve this. In short, we need to come up with the correct existence of our delta in order for us to come up with that. Because if delta cannot be properly identified here, then definitely we cannot move forward. That's very important item here. So let's start with the limit of, you have here x over x squared plus 1 as x approaches to 0, b equal to 0. This is our C, considered to be the cluster point of A. This is our f of x, and this is actually our L. So this is the intended target, and we will be guided with this. So you will have here f of x minus L is less than epsilon. In short, we need to achieve this form: x over x squared plus 1 minus 0 is less than epsilon. So once we could reach that, ultimately we'll be reaching our target. But we can simplify this further. This is the purpose of this scratch. You have x over x squared plus 1 is less than epsilon. Now, when you look at this form, okay, this form here, it's not yet very clear as to what would be the existence of delta. You need delta. Even if you're going to approach this one, that's x minus 0, which is equal to absolute value of x is less than delta. So this would be a guide for us on what our target or the final form of the delta that we will be using later. Since this here can be separated just like absolute value of x and absolute value of x plus 1. So our numerator is already okay because that's already a target here, less than epsilon. The concern now is how do we make sure that the denominator will appear as it is. In short, we will be looking for appropriate forms of our situations later. Now, how do we do this? We've been attacking the absolute value notations and its properties. What we need to do is, again, the denominator to be represented by just x itself. So this is how I would try to explain it further. Just for x squared plus 1, we know that this is always greater than or equal to 1, right? It could be 1 when x is 0, or it could be greater than for other values. Now, since this is on the denominator, once we reciprocate that, x squared plus 1, the inequality will be changing its direction to 1. Okay? So this would mean that this form here, 1 over the absolute value of x squared plus 1 is less than 1. And take note of that because we will be having that later as well. So with this now, okay, we don't need to move further because we already have the representation here. So the final form here is, if you're going to combine this relationship to our form, absolute value of x over absolute value of x squared plus 1. So this would mean absolute value of x over, not equal, because we are going to substitute now. This is less than 1, right? So that would mean this would be greater than 1, just like that. Or in short, this is absolute value of x. So the absolute value of x is still our notation here, less than delta. So the absolute value of x is less than delta, and the absolute value of x is less than epsilon, because these are all less than epsilon as taken here. So what would be the representation for our delta? Our delta could be the epsilon itself, because absolute value of x is less than delta, absolute value of x is less than epsilon. So with that, since we were able to establish that delta exists, let us go back to our proof. So we have here, let epsilon be greater than 0 and assume delta be equal to epsilon itself. So then, okay, we'll have here x minus c greater absolute value of that is greater than 0 but less than epsilon, delta, or others would automatically substitute 0 here and here, which is epsilon. You can do that, but since this is just the definition, let me stick with that. So we are going to continue here. We have the absolute value of f of x minus L represented by x over x squared plus 1 minus 0, which was able to arrive at this point here, absolute value of x over x squared plus 1, okay, which then translated into the absolute value of x, which is less than epsilon. So cutting everything short, hence you have here the absolute value of f of x minus L is less than epsilon. So we have arrived to our intended target, which is this one here. Now, we cannot claim that the limit is correct. Since epsilon greater than 0 is arbitrary, then we conclude that the limit of x over x squared plus 1 as x approaches 0 is equal to 0. This ends the proof for this limit, as we were able to establish all of this and the existence of our delta, which is equal to epsilon. We will have more examples. Thank you very much for watching.